Hello, in this lecture we will find the radius of the small circle. In the drawing we have two circles that have internal length between them at this point. Let's call this point N. Point N is the point that the two circles touch each other internally, and we also know that AC equals to 9 units, BD equals to 4 units, and also the small circle have 3 tangents. So actually this tangent is tangent to the circle at this point. Let's call this point point S. Point S is the launch point between the tangent to the circle and the circle. In this point, the circle and its tangent are touching each other. Okay, and we also have here the second launch point. Let's call the launch point Z. At point Z, the tangent is tangent to the circle at point Z. This is the point of contact between the circle and its tangent, and we also have here the third launch point between the circle and its tangent. This tangent is tangent to the circle at this point. Let's define this point M. Again, point M is the launch point between the tangent to the circle and the circle. Okay, so we will define, also we know that this is a right angle and this is also a right angle, so actually this angle is also a right angle, because along a straight line the sum of the angles are equal to 180 degrees. So if this angle is 90 degrees, the complementary angle must be equal also to 90 degrees, and this angle is also equal to 90 degrees for the same reason. And in the next step we will define the radius of the small circle as small r. Okay, small r is the radius of the small circle, and we will define capital R as the radius of the big circle. Okay, Okay. Small r is the radius of the small circle and capital R is the radius of the big circle. Okay. And we will also define as point Q. Point Q will be the center of the big circle. Again, point Q is defined as the center of the big circle, while point P will be defined as the center of the small circle. So I will write it down. Point Q is the center of the small circle, and point P is the center of the big circle. So I will read the things that I wrote. Point Q is the center of the small circle and point P is the center of the big circle. Okay, here point Q is the center of the small circle and point P is the center of the big circle. Okay, in the next step I will draw three radiuses of the small circle. The radiuses will touch at the launch points of the circle, of the small circle. Okay, so actually this radius touches the circle at the launch point, that is to say at point S. So I will write down that points S, Z, M, and M are the launch points between the circle and its tangents. I'll read again the things that I wrote. Points S, Z, and M are the launch points between the circle and its tangents. Okay? Points S, Z, and M are the launch points between the circle and its tangents. This is the first tangent, this is the second tangent, and this is the third tangent. So those points S, M, and Z are the launch points between the circle and its tangents. Okay? Then I will draw the second tangent, the second radius to that touches the circle at the launch point, that is to say the radius will touch the circle at point Z. this is the radius that touches the circle at the launch point, point Z, and then I will draw the third radius that also touches the circle at the launch point. That is to say, it touches point M. That is the launch point. Okay? So actually we have a rule number 1. According to rule number 1, the tangent to the circle, the tangent to the circle is perpendicular to the radius at the launch point. So I will read rule number 1 again. Rule number 1 states that the tangent to the circle is perpendicular to the radius at the launch point. So actually here we have the radius that touches the circle at the launch point. It touches the circle at point S. It actually touches point S. So according to rule number 1, the tangent to the circle is perpendicular to the radius at the launch point. So this tangent is perpendicular to the radius at the launch point. The radius is drawn to the launch point, that is to say, is drawn to point S, and for that reason the tangent is perpendicular. The tangent is perpendicular to this radius. That is to say, this angle is a right angle. It equals to 90 degrees. Okay, again, according to rule number 1, the tangent to the circle is perpendicular to the radius at the launch point. So this tangent to the circle, this tangent is tangent to the circle at point S. Point S is the launch point, and according to rule number 1, that this tangent to the circle is perpendicular to the radius at the launch point. Because of the fact that the radius is drawn to the launch point, that tangent is perpendicular to that radius that is drawn to the launch point. That is to say, the radius that is drawn to point S, that is the launch point, the tangent is perpendicular to this radius. That is to say, this angle is a right angle. It equals to 90 degrees. Okay, and we have the same thing also here at point Z, that is the launch point. The radius is drawn to the launch point. Actually, this radius touches the launch point. This radius touches point Z, that is the launch point. Therefore, according to rule number 1, the tangent is perpendicular to this radius that is drawn to the launch point. So this angle is a right angle. It equals to 90 degrees. Again, because of the fact that the radius is drawn to the launch point, then the tangent is perpendicular to the radius, that is to say this angle is a right angle, it equals to 90 degrees. And the same thing is also here, that radius is drawn to the launch point, that is to say is drawn to point M, that is the launch point. Actually it touches point M, that is the launch point. For that reason, this tangent is perpendicular to the radius that is drawn to the launch point. So this angle is a right angle, and also this angle is a right angle. So whenever you draw a radius that touches the launch point and a radius that is drawn to the launch point, then the tangent will be perpendicular to that radius. So here we have three radiuses that touch the launch points. They are drawn to the launch points, therefore they are perpendicular to their tangents. So this is a right angle, this is a right angle, and also this is a right angle, according to rule number 1. Okay, so if you draw a radius to the launch point, a radius that is drawn to the launch point, then the tangent will be perpendicular to that radius, or the radius will be perpendicular to the tangent. It is the same thing to say. So actually we have here a quadrilateral QZMD that has three right angles. Okay, I'll write it down. Quadrilateral QZMD has three right angles. That the sum of them equals to 3 times 90, that equals to 270 degrees. Okay, the sum of the angles inside quadrilateral QZMD equals to 270 degrees, the sum of the three angles that are right angles. So the fourth angle, what is the size of the fourth angle? Actually, we have a rule that states, rule number 2, rule number 2 states that the sum of the angles in a quadrilateral equals to 360 degrees. So I will read rule number 2 again. rule number 2 states that the sum of the angles in a quadrilateral equals to 360 degrees. The sum of the angles in a quadrilateral equals to 360 degrees. So actually we have three angles. The sum of the three angles is 270 degrees. So the total angles, the sum of the total angles, we have three angles that the sum of them is 270 degrees, and the x or y will be the size of the fourth angle. The size of the fourth angle will be defined of Q. Okay, angle y is the variable that is defined as the size of the fourth angle inside the quadrilateral QZMD. So according to rule number 2, the sum of the angles in a quadrilateral equals to 360 degrees. So actually the sum of the four angles inside quadrilateral QZMD will be equal to the sum of the three angles, that equals to 270 degrees, plus the size of the fourth angle, and in total the sum of the four angles inside quadrilateral QZMD must be equal to 360 degrees. Okay, according to rule number 2, the sum of the four angles inside quadrilateral QZMD must be equal to 360 degrees. So we have three angles that the sum of them is 270 degrees. So if we add the fourth angle, in total the sum of those four angles must be equal to 360 degrees. Okay, so from this equality we'll subtract that 270 degrees from this equality, and we will get the value of y equals to 90 degrees. Okay, so we concluded that the size of the fourth angle is 90 degrees, that is to say it is a right angle. So this angle is a right angle. So So actually the size of the fourth angle inside quadrilateral QZMD is 90 degrees. That is to say, it is a right angle. So quadrilateral QZMD has 4 right angles. Okay, I'll write it down. Quadrilateral QZMD has 4 right angles. Okay, quadrilateral QZMD has 4 right angles, and we have rule number 3. Rule number 3 states a quadrilateral that has 4 right angles is a rectangle. I will read rule number 3 again. Rule number 3 states that a quadrilateral that has 4 right angles is a rectangle. So, according to rule number 3, quadrilateral QZMD is a rectangle. Okay, according to rule number 3. I will read again the things that I wrote. Quadrilateral QZMD is a rectangle according to rule number 3. And we also have rule number 4 that states so rule number 4 states that the opposite sides of a rectangle are equal to each other. I will read rule number 4 again. Rule number 4 states that the opposite sides of a rectangle are equal to each other. So actually, according to rule number 4, we know that quadrilateral QZMD is a rectangle because it has 4 right angles. According to rule number 3, it is a rectangle. Therefore, according to rule number 4, that the opposite sides of a rectangle are equal to each other, QZ, that is opposite to MD, equals to MD. Okay. QZ equals to MD according to rule number 4, that states that the opposite sides of a rectangle are equal to each other, so QZ equals to MD. Okay. QZ equals to MD. But QZ is defined as a radius, so QZ equals to R. QZ is the radius of the small circle. Okay, QZ equals to small r because QZ is the radius of the small circle. Okay, so we got this equality that r equals to QZ equals to MD, so we can derive from this equality that r equals to MD. Okay, r equals to MD. So actually MD is the radius of the small circle. It equals to R according to our proof. Okay, actually we have here second quadrilateral SQCM. Okay, this quadrilateral is SQCM. Okay, and we will repeat on the same process in order to prove that CM equals to the radius of the small circle. We have quadrilateral SQCM that has 3 right angles. Therefore, according to rule number 2, that the sum of the angles in a quadrilateral equals to 360 degrees, the fourth angle must be equal to 90 degrees. This is a right angle. So quadrilateral SQCM has 4 right angles. So according to rule number 3, if a quadrilateral has 4 right angles, it is a rectangle. So quadrilateral SQCM has 4 right angles, and therefore according to rule number 3, it is a rectangle. Okay, this quadrilateral is a rectangle, and we have rule number 4 that the opposite sides of a rectangle are equal to each other. That is to say, SQ equals to CM. And we know that SQ equals to R. Therefore, CM that equals to SQ will be also equal to R. Okay, so CM equals to R, small r. Okay, we actually proved that MD equals to small r and CM also equals to small r. In the next step, we will define line segment PM as X. Okay, line segment PM will be defined as X. Okay, I write it down. Line segment PM equals to X according to our definition. This line segment PM equals to X. So what is the value of CP? The value of line segment CP. CP equals to CM minus PM. CM minus PM. Again, line segment CP will be equal to CM minus PM. CP line segment CP will be equal to CM minus PM. Very simple. But what is the value of CM? CM equals to R. Okay? And what is the value of PM? PM equals to X according to our definition. Okay, so CP will be equal to R minus X. Okay? CP equals to CM minus PM, and CM equals to small r, and PM equals to X, so CP equals to R minus X. Okay, so I write it down that in the drawing that CP equals to R minus X. Here CP equals to R minus X. Okay? Here CP equals to R minus X. So in the next step we will calculate the size of the radius of the big circle in two ways. We know that AB is the diameter of the big circle. That is to say, AB equals to 2 times capital R. And actually, AB, the size of AB, is AP plus PB. Okay, so the size of AB, that is the diameter of the big circle, is 2 times the radius of the big circle, that is to say, is 2 times capital R. And AB, actually, AB equals to AP plus PB, because P is the center of the big circle. Okay, AB equals to AP plus PB. AP plus PB, and AP equals to R, capital R, and PB equals to capital R also. Okay, so AP equals to capital R plus capital R. Okay, so we will create the first equation that states that AP equals to capital R, that is to say AP is the radius of the big circle. Okay, AP equals to capital R, it is the radius of the big circle, and our second equation will be that PB also equals to capital R. It is the radius of the big circle. Okay, PB also equals to the radius of the big circle, that is to say it equals to capital R. Okay, then we will return to equation number 1 that AP equals to R, and we will calculate the value of capital R, the radius of the big circle. So according to equation number 1, AP equals to capital R, but what is the value of AP? AP actually equals to AC plus CP. Very simple. AP equals to AC plus CP. Okay, AP equals to AC plus CP. Okay, but what is the value of AC? AC equals to 9 units according to what is given us in the question. AC equals to 9 units. And what is the value of CP? We have already found out that the value of CP is small r minus x. So in total we got that AP that equals to R equals to 9 plus small r minus x. Okay, so we can write down that the radius of the big circle capital R equals to 9 plus r minus x. That is our first equation. Then we have our second equation that PB equals to R. Okay, according to our second equation, PB equals to capital R, that is the radius of the big circle. But what is the value of PB? What is the value of PB? PB equals to PM plus PM plus MD plus dB. Okay, plus dB. Again, PM equals to PM plus MD plus dB. Okay, according to the drawing, PB equals to PM plus MD plus dB. Okay, but what is the value of PM? PM equals to X according to our definition, and what is the value of MD? MD equals to R. We found out that MD equals to small r, that is the radius of the small circle, plus dB. What is the value of dB? dB equals to 4 units. It is given us in the question. So in total we got that PB that equals to the radius of the big circle equals to X plus small r plus 4. So I will write it again that according to equation number 2, the radius of the big circle equals to X plus small r plus 4. Okay, according to equation number 2, the radius of the big circle equals to X plus small r plus 4. But according to equation number 1, the radius of the big circle equals to 9 plus small r minus x. Okay, according to equation number 1, the radius of the big circle equals to 9 plus r minus x. So here we have two expressions of the same radius. So of course they are equal to each other. So we will compare equation number 1 to equation number 2, and in this way we will create equation number 3. So equation number 3 will state that capital R equals to capital R. Okay? Capital R according to equation number 2 equals to capital R according to equation number 1. Okay? So we will get that equation number 3 will state that capital R, that is x, plus small r plus 4 equals to capital R according to equation number 1, that is 9 plus small r minus x. Okay, we got equation number 3 that states that capital R equals to capital R. So here we have r in this side, small r in this side of the equation, and we have small r in the other side of the equation, so we can cancel r. R is cancelled. What left after we cancelled r? So after we cancelled r, what is left is x plus 4 equals to 9 minus x. Okay, after we cancelled r, what is left is x plus 4 equals to 9 minus x. Here we will subtract 4 from this equation number 3, and we will get that x equals to 9 minus 4 is 5 minus x. Okay, we got that equation number 3 states that x equals to 5 minus x. Here we will add x to this equation, and we will get that 2 times x equals to 5. Okay, we got the equality that states that 2 times x equals to 5. Here we will divide this equality by 2 in order to get the value of x. Okay, so x will be equal to 5 over 2. 5 over 2 is 2.5 units. We got that x equals to 2.5 units. So expression number 1, that is for the radius of the big circle, states that x plus minus x plus 9 plus r, or capital R, equals to minus x plus 9 plus small r. That is actually equation number 1, but we know here that x equals to 2.5 units, so we can substitute x by 2.5 units, and we will get that capital R equals to minus 2.5 plus 9 plus R. We got that the radius of the big circle equals to minus 2.5 plus 9 plus R. So 9 minus 2.5 is 6.5. So we got that the radius of the big circle, according to equation number 1, equals to 6.5 plus small r. So we have the radius of the big circle, it equals to 6.5 plus small r, or we can say that the radius of the big circle is bigger at 6.5 units than the radius of the small circle, and we know that x equals to 2.5 units. Okay, so in the next step I will present rule number 5, and then we will implement rule number 5 in our drawing. So rule number 5 states if two circles have internal lunge between them, then the distance between their centers is equal to the difference between the lengths of their radiuses. So I will read rule number 5 again. Rule number 5 states that if two circles have internal lunge between them, then the distance between their centers is equal to the difference between the lengths of their radiuses. I will read rule number 5 again. If two circles have internal lunge between them, then the distance between their centers is equal to the difference between the lengths of their radiuses. So actually, if we have two circles that have internal lunge between them, that is to say, if two circles touch each other internally, then according to rule number 5, the distance between their centers, the distance d between their centers, is equal to the difference between the lengths of their radiuses. So if the radius of one circle is is r1, and the radius of the other circle is r2, then the difference d between their centers will be equal to r1 minus r2. Okay, so we actually can implement rule number 5 in our drawing, because we have here two circles with an internal length between them at point N. They touch each other at point N. They have internal length between them at point N. So according to rule number 5, the distance between their centers, that is to say PQ, because Q is the center of the small circle and P is the center of the big circle, so the distance between the centers of the two circles is PQ. So this PQ, according to rule number 5, PQ equals to the difference between the lengths of their radiuses. Okay, it equals to the difference between the lengths of their radiuses. The length of the big radius is capital R, while the length of the small radius is small r, so the difference between those radiuses is capital R minus small r. So in total we got equation number 4 that states that PQ, that is the distance between the centers of those two circles, is equal to the difference between the lengths of the radiuses, that is to say it equals to capital R minus small r. Okay, here we can add small r to this equation, and we will get that capital R equals to PQ plus small r. Okay, we got the radius of the big circle equals to PQ plus small r. But we have equation number 1 that states that the radius of the big circle, that is to say capital R, equals to 6.5 plus small r. Okay, so we have here two different expressions for the same radius, and of course they are equal to each other because we are talking of the same radius. So we can compare equation number 4 to equation number 1. Okay, and we will get equation number 5 that states that capital R equals to capital R, or PQ plus small r equals to 6.5 plus small r. Okay, equation number 5 states that capital R, according to equation number 4, equals to capital R according to equation number 1. Here we have small r in this side of the equation, and we have small r in the other side of the equation, so we can cancel r. And after we cancelled r, we got that PQ equals to 6.5 units. PQ equals to 6.5 units, and we already know that X equals to 2.5 units. So we can, in the next step, we will connect together points P and Q by a straight line. Actually, triangle PQM is a right triangle. The green triangle is a right triangle because of the fact that angle QMP is a right angle, therefore triangle QMP is a right triangle. So we know that the hypotenuse of this right triangle QP or PQ equals to 6.5 units. We know that PM that equals to X equals to 2.5 units, and the only missing variable is the radius small r, the radius of the small circle. So we can find the radius of the small circle, that is to say small r, according to the Pythagorean theorem. Okay, so we will implement the Pythagorean theorem on the right green triangle PQM. Okay, on triangle PQM, according to the Pythagorean theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The square of the hypotenuse is PQ square equals to the sum of the squares of the perpendiculars equals to PM square plus QM square. So the implementation of the Pythagorean theorem in the right triangle QMP gives us that PQ square equals to PM square plus QM square, or the square of the hypotenuse equals to the sum of the squares of the perpendiculars. But we know that PQ equals to 6.5 units, so PQ square will be equal to 6.5 square. And we know that PM equals to X, and X equals to 2.5 units. So PM square is 2.5 square plus QM square. QM is the radius of the small circle, so we can write here that QM square equals to R small r square. So in total we got that 6.5 square equals to 2.5 square plus small r square. 6.5 square is 42.25 units, and it equals to 2.5 units is 6.25 units plus r square. So we got that 42.25 equals to 6.25 plus r square. Here we will subtract 6.25 from this equality, and we will get that 42.25 minus 6.25 equals to 36. So 36 equals to r square. So here we will take a root out of this equality, and we will get that small r, that is the radius of the small circle, equals to root of 36. Root of 36 is 6. So we found out that r small r, that is the radius of the small circle, equals to 6 units. Again, the radius of this small circle equals to 6 units. Okay, so that is the answer to the question. Now I will summarize the lecture. Actually, we wanted to find out the radius of this small circle, and we have here two circles that have internal length between them at point N. And actually, the small circle has three tangents. This tangent is tangent to the small circle at point Z. This tangent is tangent to the circle at point M, and this tangent is tangent to the circle at point S. And we actually drew three radiuses that starts from the center of the circle and touches the launch points in this circle. Actually, this radius touches the launch point, that is to say point Z. This radius also touches the launch point, that is to say point M, and this radius also touches the launch point, that is to say touches point S, that is the tangent, is tangent to the circle at point S. Okay, so actually we have a rule. It is rule number 1 that states that the tangent to a circle is perpendicular to the radius at the launch point. Okay, so again, rule number 1 states that the tangent to the circle is perpendicular to the radius at the launch point. Okay, actually this tangent to the circle is perpendicular to the radius at the launch point. So if the radius touches the circle at point S, that is the launch point, then this tangent is perpendicular to this radius. That is to say, this angle is a right angle. And also here we have radius that touches the circle at the launch point. It is drawn to the launch point, that is to say to point M, that is the launch point. Therefore the tangent is perpendicular to that radius. And also here, this radius is tangent to this radius touches the circle at point Z, that is the launch point. This radius is drawn to the launch point, that is point Z. Therefore this tangent is perpendicular to that radius. That is to say, this angle is a right angle. Okay, so actually whenever a radius touches the circle at the launch point, then the tangent is perpendicular to that radius. So all these angles are right angles, according to rule number 1. Okay, so actually we have here quadrilateral QZMD that has 3 right angles, and the sum of the 3 right angles is 90 times 3 is 270 degrees. And we have rule number 2 that states that the sum of the angles in a quadrilateral equals to 360 degrees. Okay, so we know that the sum of the three angles inside quadrilateral QZMD equals to 270 degrees, and according to rule number 2, the sum of the four angles inside the quadrilateral equals to 360 degrees. So 270 degrees, that is the sum of the three angles, plus the size of the fourth angle must be equal to 360 degrees according to rule number 2 that states that the sum of the four angles inside the quadrilateral equals to 360 degrees. Okay, so in total the sum of those four angles must be equal to 360 degrees. So 270 degrees plus y must be equal to 360 degrees. Here we subtracted 270 degrees from 360 degrees, and we got that y, that is the size of the fourth angle, equals to 90 degrees. That is to say, the fourth angle is also a right angle. So here, this angle is a right angle. So actually, we have here a quadrilateral that has four right angles, and according to rule number 3, a quadrilateral that has four right angles is a rectangle. Okay, according to rule number 3, a quadrilateral that has four right angles is a rectangle. So this quadrilateral QSMP has four right angles, and therefore, according to rule number 3, this quadrilateral is a rectangle. Okay, QZ MD is a rectangle. Okay, and we have rule number 4 that states that the opposite sides of a rectangle are equal to each other. So actually, according to rule number 4, QZMD, that is a quadrilateral, has two opposite sides that are equal to each other. That is to say, QZ is equal to MD. Okay, QZ equals to MD according to rule number 4, that the opposite sides of the rectangle are equal to each other. But we know that QZ is the radius of the small circle, so QZ equals to small r. So from this equality, that r equals to z equals to MD, we can derive the equality that r equals to MD. So we found out that r equals to MD. This is MD is the radius of the small circle. It equals to small r. Okay, and then we actually have very similar quadrilateral. SQCM is quadrilateral with three right angles. So according to rule number 2, that the sum of the angles in any quadrilateral equals to 360 degrees, the fourth angle must be also equal to 90 degrees. So we have here a quadrilateral with four right angles. Therefore, according to rule number 3, that if a quadrilateral has four right angles, then it is a rectangle. So quadrilateral SQCM that has 4 right angles is a rectangle according to rule number 3, and according to rule number 5, that the opposite sides of a rectangle are equal to each other. SQ equals to CM, but we know that SQ equals to small r, so CM also must be equal to small r. So we have here MD that equals to small r and CM equals to small r. We defined PM as x, so CP must be equal to CM minus MP, that is to say CP equals to R minus X, and then we created two equations for the radius of the big circle. Actually, AB is the diameter of the big circle, it equals to 2 times R, that is to say it equals to AP, that is capital R, plus PB, that is also capital R. So we created two expressions for the radius of the big circle. The first equation is AP equals to R, to capital R. AP, P is the center of the circle, so AP equals to capital R is the radius of the big circle. That is the first equation, and the second equation is PB also equals to capital R. PB is also the radius of the big circle. So we have here two expressions for the same radius, that is the radius of the big circle. From the first expressions, we got that capital R equals to 9 plus small r minus x, and from the second expressions that states that PB equals to R, we got that capital R equals to X plus small r plus 4. So here we have two different expressions for the same radius. So of course they are equal to each other because we are talking about the same radius. So equation number 1 equals to equation number 2, or capital R equals to capital R. That is equation number 3 that states that capital R equals to capital R. And from equation number 3 we got that X, that actually it is MP, this is PM, X that equals to PM is actually equals to 2.5 units, and we have equation number 1 that states that capital R equals to 6.5 plus R. Actually we substituted the X by 2.5 units because X equals to 2.5 units, to 2.5 units. We substitute that X by 2.5 units, and we got that capital R equals to 6.5 plus small r. Okay, so we have this equation number 1 for the radius of the big circle, and then we presented rule number 5 when we implemented rule number 5 on our two circles. According to rule number 5, if two circles have internal length between them, then the distance between their centers is equal to the difference between the lengths of their radiuses. So if two circles touch each other internally, then the distance between their centers equals to R1 minus R2, or D equals to R1 minus R2. That is the difference between the radiuses. Okay, so we implemented rule number 5 in our two circles because we have here two circles that have internal length between them at point N. They touch each other at point N internally. So according to rule number 5, the distance between their centers, according to rule number 5, the distance between their centers, that is QP, because Q is the center of the small circle and P is the center of the big circle. So QP is the distance between their centers. This distance equals to the difference between the lengths of their radiuses. The length of the big radius is capital R and the length of the small radius is small r, so the difference between the radiuses is capital R minus small r. So actually we have the equality that states that PQ equals to capital R minus small r, that is to say the distance between their centers, that is PQ, equals to difference between their radiuses. That is to say, PQ equals to capital R minus R. So from this equation we got that capital R equals to PQ plus R. But we have equation number 1 that states that capital R equals to 6.5 plus small r. So we have two expressions from the same radius. And they, of course, are equal to each other because they are expressions for the same radius. So we compare the equation number 1 to equation number 4. That is to say, equation number 5 states that capital R equals to capital R. So from equation number 5 we got that PQ equals to 6.5 units, and we have already found out that X equals to 2.5 units. Okay, so here we connected together points P and Q by a straight line, and the green triangle is a right triangle because of the fact that angle QMP is a right angle. Therefore triangle QMP, the green triangle is a right triangle. So we can implement the Pythagorean theorem in the green right triangle QMP. According to the Pythagorean theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, QP square equals to PM square plus QM square. Okay, QP square equals to PM square plus QM square, but we know that PQ equals to 6.5 units and PM that equals to X equals to 2.5 units. And QM is the only variable that is missing, that is actually the radius of the small circle. So we solved this simple equation with only one variable, and we found out that the radius of the small circle equals to 6 units. Okay, actually the answer to the question is that the radius of the small circle equals to 6 units. Okay, thank you very much.